Alright, welcome back. In today's video we're going to look at LEDs. So it's similar to the diodes that we've looked at, except there's one main difference now. The LED outputs light when we pass current through it. Now if we look at our common diode circuit here, we could simply set up a KVL to find that the current is equal to our source voltage minus 0.7 divided by our resistor. And if we look at the power dissipated of the diode, or P subscript D, it's going to be the voltage of the diode times the current of the diode, and all that power is going to go to heat. Now let's consider an LED. Can we use the same rules here? Well, not really. We cannot really use the same current approximation for one simple reason. The voltage drop right here is 0.7 volts that we assume is an approximation for a common diode. That's not the voltage of the LED. Now we have many different kinds of LEDs. If we look at a few here, we have a red or red-orange LED here. So we have the IV curves for multiple different colors. That's what we're looking at. We have a green LED here, and then right here we have kind of two overlaying curves. We have a royal blue or PC blue, and then a PC amber. Now the PC term in front of these colors stands for phosphor converted, and we'll deal with LEDs very in depth when we start to talk about optics. But for now, we're just going to know that the PC term here stands for phosphor converted. Now we can generalize the forward voltage for all of these different color LEDs. And what you might see if you look online is that for a red LED, it's going to be approximately equal to 2.2 volts. For yellow, it's going to be about 2.2 volts. For green, it's going to be 3 volts. For blue, 3.3 volts. And then for white, you might see all the way up to 3.5 volts. Now, the reason that you'll see this is because each different LED is made with different materials. Again, the material science and the semiconductor physics that goes into all of this, very complex, but we'll get there. If we look at a red LED, it's going to be made of a combination of aluminum, right here, indium, gallium, and then we have a phosphide. Now, if we look at the yellow LED, we have gallium and arsenide, and then a phosphide. If we look at green, we have indium, gallium nitride, or commonly referred to as InGaN. And you might also see that red is referred to as an Allen gap LED. But then if we look at blue, you can have two different variants. You can have a GaN or an InGaN combination to get blue. And then if we look at the white LED, you get something interesting. You have InGaN here, and then you have yellow phosphor. And we notice that the InGaN shares a resemblance to that blue LED. So what's going on to generate white light? Well, what happens is that when we use that InGaN material, it provides blue light. Now we're going to couple that to yellow phosphors, and they're going to emit different wavelengths, and that's how we get our production of a white LED. So a white LED starts as a blue LED. Now with white LEDs, you can have things called color temperature, which if you ever went to a light bulb section at any kind of store, you've seen warm white and cool white, most likely. Those refer to the color temperature. So you can go much larger range than 5700 Kelvin and 3000 Kelvin, but that's just what we're looking at here in these graphs. And you'll notice that the warmer color temperature, so something like 3000 Kelvin, it has a lot more contributions from, per se, green and red light as compared to the cooler light source, which is 5700 Kelvin. Now if we looked at the spectral information for each one of our colors, that's given here on the right. So you can see in the 430 to 480 nanometer wavelength, we get our blues. So what we can say is that phosphors can add color additives or additions, and this is what's going to help us create white light. So if we scroll back up here, we saw that we had this PC amber and this PC blue, or phosphor converted. So we used phosphor to actually make an amber in this case. Now maybe you ask, why do you even want a PC amber LED? Well, it turns out thermally, if you look at the output characteristics of the LED, you have a clear distinction. But moving on, we can get back to our original circuit. So instead of saying that we had the 0.7 voltage drop here, we replace the voltage of the diode simply as the voltage over the LED. And in our case, we're just going to assume that to be 2.2 volts, and we follow through in a similar fashion. Now something that's very useful is if we consider the electrical power to this LED, which is going to be denoted by P subscript EL, and that's going to be equal to the current times the voltage over that red LED. Now recall that this power didn't all go to heat. We get some light out of it. And we're going to say on a good day, on a real good day, let's say the optical efficiency of that LED is 40%. So the optical power is approximately 40% of the electrical power, which means that 60% of the electrical power that's going to heat. Versus the common diode, where you had 100% of the electrical power going to heat. So what we can really say is that the LED, when it's in a very good mood, it'll be 40% efficient. Now 40% seems pretty bad, but if we compare this to something like incandescent lights, we're looking at, on a good day again, about 15% efficiency. So extracting light from electronics is a very unique and difficult process. Now if we look at a few other characteristics of an LED, so here on the left, we're going to look at the deviation in the voltage as we increase temperature. And what you can see is that the voltage of the LED decreases as temperature increases. And we have room temperature about somewhere here at 25C. Now a game you play is that the more drive current you push through that LED, you're going to have more heat. It's going to actually heat up the junction of that LED. So not only will you decrease the forward voltage, which can lead to this current runaway issue, you will also be decreasing the lumens, or the light per se, that you're outputting of the LED. So on the right here, we're looking at the flux denoted by this. So that's going to be the lumens value. And then horizontally, we're looking at the junction temperature. So if we mark our point at about 25C, you can see that it's quite normalized here. And if we heat up that junction, you can see that we have a pretty quick decrease in the lumens. So not only does the thermal impact potentially cause this runaway current issue, that runaway current is going to heat up your device, and as that device heats up, it's going to be less and less efficient. And this is one of the big areas of research is how can we make the most efficient LED that's also cost effective? So overall, getting light out of electronics it's pretty hard. One thing that's very interesting is something called the LED photovoltaic effect. So we know that we can pump some current through the LED and it's going to output light, but if you shine light onto that LED, you can also produce a current. Now in the next video, we're going to talk about transistors, which is kind of the bread and butter of this course. Again, it's a semiconductor, but we don't have to talk about them in this video. We can get to it later on. But if you learned anything useful, anything important, please like, comment, share, subscribe. Helps the YouTube algorithm. We'll see you in the next video.